here in the morning, so I'm going to repeat this. There's a workshop channel in the Discord, and that will ease, not only to send out the links and resources to you guys. So make sure to join the Discord and see that workshop channel, and you'll be able to see the microphone. This microphone sometimes it's just like yeah, I held it too far. So so join the channel and then we'll send the resources. Where's the channel link? Sorry? Where's the channel link? The channel. So go to the ETHTaipei organization and there's a Discord, right? So join the Discord first, and there should be a workshop channel. retro rock and roll seats. There are seats. Yeah. Like 3, 4, I'm taking 5 seats.
Stay here.
So just a reminder to join the Discord and the workshop channel. All right, so it's easier to share the resource there. So I believe Natalie already shared some resource there, so you'll see the link to the repository. Along the way, if you have some side questions that you don't want to drop emails or send it there. But yeah, mainly for the resource center. Definitely join the workshop channel.
Natalie, did you share the link in the workshop channel?
Yeah.
I see it.
Installing.
Yeah, it's gonna take a while. It's still installing.
And then after we start the exercise, or?
There's a link in the Discord channel.
Oh yeah, I got it. And then we do the exercise.
Do we donate to I'm not sure.
we mainly do a bit of kind of security reviews, security research, and that goes into not just blockchain, but also across applications. So that's including like application security, cryptography, and a variety of other things. You might have heard of Trilobits through some of our tooling. We do have a lot of open source software. Some of that is static analysis for Further, fuzzing with Echidna, as well as support for other blockchains. In some, you'll see Tealer for Algorand, Amarna for StarkNet and Cairo, and Solxi Select for kind of tooling for the Ethereum space. Before I start, I just want to get kind of an idea of kind of the audience and who's here. So from, I guess, raise your hand if you are a developer writing smart contracts and writing your facility-based contracts on a daily basis. So I guess for those of you who raise your hand, this. Okay. For those of you who raise your hand, this is kind of this tutorial and kind of this workshop is going to be very heavily Solidity-based, and so this is a chance for you. This is a chance for you to kind of follow along and run code if you want. From in terms of fuzzing, I'm going to start off with kind of a very high level. How do we find bugs in smart contracts, and what we look for when we implement property-based testing. We're also going to look at how to find invariants and what we look at when we start looking at how to implement system invariants. And then we're going to go into some live demos and interactive opportunities for you to get a chance to actually write invariants of your own and be able to kind of get a feel for how you can actually implement. So to start off, I started off with kind of this first slide of installing Echidna. So Echidna, you can install it if you're on a Mac. You can just install it using brew, just using that first command, brew install Echidna, and this should work for the recent M1, M2 as well. If you're on Linux, you can install it through Nix, and if there are some Windows binaries that are also available, on Critic. I'll just pause for a minute or so to give you a chance to install it first. I also posted a link to the Building Secure Contracts branch that has these slides as well as the exercises that we're going to be going through in the workshop Discord. So if you want to follow along with slides, you can there, as well as actually running the examples that we'll be going through today. All right, let's do a quick gut check. How many of you have installed Echidna? I'll just wait another 30 seconds or so. then we can get started.
Are you using ETHTaipei Wi-Fi?
Yeah, you need the password.
What's the password?
Can dash do something with a capital C.
Can devs do something with a
Capital, the first letters capital.
with a question mark? Last.
All right, so from that Discord link, I did also link a GitHub repository, which has the examples that we'll be working off of. It's not ideal that this is in a slide, but if you clone that repository and check out the ETHTaipei workshop branch, this will allow you to follow along. This is also the same link as the Discord, so if you just want to clone directly from GitHub there, that works. How many people have cloned the GitHub repo? Right. And I'm going to get started into kind of how to find bugs in smart contracts and how to use tooling that's available within the industry in order to maximize the amount of, or the number of bugs that we find and the complexity of them. So if we take a step back and look at how we can find bugs in code in the first place, a lot of that ties back into kind of the testing through either unit testing or manual analysis. So unit testing is kind of the expectation that you have unit tests and integration tests on your code base, whereas manual analysis and automated analyses kind of take a different look at your code, a different view. So with fully automated testing, what you'll find is that this is something that you can run on your code base, and it will show you many different findings. This is something that is generally something that, like Slither, that you don't necessarily need to run your code. It will just analyze your code for you and spit out a bunch of different findings, which requires you as a developer or a security researcher to be able to go through and hit and kind of verify the output as well as what the results are. Which means that from the perspective of actually looking through these results, it often requires triaging and going through a bunch of results. It also requires you to actually understand the system and kind of the context that you're going to be using that smart contract in. This is one example of fully automated testing in which you can run Slither on a smart contract and it will show you, for example, all the results in the smart contract that might result in rate increase. Whether or not they're actually exploitable, that's something that as a developer or researcher you need to go through and kind of manually comb out what's realistic and what's not. other side of automated analysis is semi-automated. So this is really good for kind of identifying potential bugs that result in, as a result of logic errors or arithmetic, for example. But it does require kind of someone to be able to go in and write those invariants, specify what is expected of a system, and it requires you to think a little bit differently about your code, at least in a different way compared to unit testing. Echidna is going to be the topic of today's conversation in this workshop. Before I go in more into kind of property-based testing, any questions about, I guess, the different types of analyses that you can do on a smart contract so far? Or I guess about Echidna as well. All right, perfect. So in terms of fuzzing, this is what we're going to be focusing on today. And if we take a very high level look at what fuzzing is, it's basically stressing a program with random inputs. So if you were to take the most simplest implementation of a fuzzer, it would basically be like a cat typing on a keyboard and seeing, how your code handles that random input and whether it behaves as you expect. So another example of this that doesn't involve a cat is like randomizing input in like a unit test. This is somewhat similar to the similar concept of basically taking random input, throwing at the smart contract, and seeing, is it possible for invariance to break in some way? So fuzzing in general is something that has been implemented fairly commonly in traditional software. You can see that with especially libfuzzer and gofuzz. You can see this for other languages. The only thing is they usually test for crashes. So this is when your program just can't handle an input and therefore fails. You don't necessarily have crashes in smart contracts. Smart contracts just don't allow you this ability. So with property-based testing, it's slightly different because as a user, we essentially need to define invariance. We need to specify what is expected behavior so that we can actually tell a fuzzer like Echidna what is expected and what is not expected. And so from a perspective of the fuzzer, we're basically going to be generating random inputs in order to check these assumptions that we've specified on the system. So if we go back to the example of unit tests, then it's basically like unit tests on steroids. Because with unit tests, we test kind of a subset and smaller area of the system, but as long as we increase the randomness aspect, then we're able to hit more corner cases with fuzzing. So that brings an interesting question as to how are we supposed to think about code bases and how do we actually specify invariance? Well, that kind of requires us to know what an invariant is and how we can even think about it. Because we don't usually think about code in terms of invariance. We think of code in terms of this function's supposed to do this. And so this is the expected behavior of a function. When in fact, we might be able to actually slightly change the way that we think about that in order to kind of specify an invariant when we're talking about it. So an invariant is basically something in a system that should always be true. It's something that should hold true regardless of user input, regardless of how a user interacts with your system. So that's a little bit vague. I'm going to be going more into examples of invariants and how to think about that in different code bases. But using Echidna, we can basically take the concept of how is the code expected to behave and execute it on top of smart contracts in order to find potential deviations. So Echidna is our smart contract fuzzer. It is open sourced and it's used in a lot of kind of mature code bases, ones who have a fair number of unit tests and kind of they know what the expected behavior of their system is. The Echidna repository also has some examples of more complicated integration with Echidna in case you want to take a closer look at how complex test suites look. So I'm just going to start off with the first exercise that's in that GitHub repo. So exercise 1 is basically, I'll walk through kind of the code and what we want to check first. So let's take if we take a look at that code, what it's implementing is basically a token. It's implementing kind of the underlying expectation. It's operating on a token, and one potential invariant that we can say with respect to token balances, or user balances in general, is that a user balance should never actually exceed the total number of tokens in circulation. If it ever does, then we know there's definitely some kind of arithmetic issue, or there is a logic issue within this contract. So if we think about this token and the invariant, the invariant is basically that the user balance should never exceed the total supply of tokens in the market. So one thing that we need to kind of analyze here. So I'm just going to share this as well. So this, the exercise already has code for the token, and the token is basically implementing this transfer function. When we create this S token, we're basically initiating it with an initial supply, in this case of 10,000. When we write properties in Echidna, one of the ways to do it is by just creating a function in Solidity with this Echidna underscore prefix. And what this will do is basically tell Echidna that there is a property that is expected to run here, and to tell Echidna to look out for something. So if I were to run this with Echidna right now, it's just going to tell me that there are no tests that are found because the body of this function is empty. So I'll give you 10 minutes just to try to figure out how considering you write invariants using, assuming that you have an Echidna prefix, Echidna is basically going to look for a return value of false, and that's going to essentially identify that there is a property violation. So assuming we did just return false here, Echidna is essentially just going to immediately flag this function as an invariant failed. But instead of returning false, we want to make use of the variables within this token contract and this test token to basically add the property that user balance shouldn't exceed. Alright, so in order to run this file, you can basically go into that directory, and then assuming you've already had Echidna installed, you can run this directly on the template. So Echidna template. This also does rely on you having SilkC installed for a certain version. So this one assumes version 0.5, which we can run. SilkC select is basically allows you to change SilkC versions. So in here we're basically changing the global SilkC to 0.5. And then we can run directly on the template. This is going to be the output of Echidna, of what it looks like right now when we just return false. It's basically going to say no transactions were made because it immediately found the false return value, and then it just halted because it effectively already found a property violation.
Manage to get it to work? You have to install SilkC select.
Yeah, well, I don't know what's it? It's supposed to be less than total supply, right?
Yeah, but there isn't a total supply variable. So I just tested it against 10k. Let's equal 10k. Because it's the initial balance.
Okay, that makes sense. I was looking,
Yeah, I know, there's no total supply variable.
Yeah, toilet. Me too.
If you are getting a SOCC select error, you can run pip3 install SOCC select. This will essentially download the SOCC select library. And then I'll post the other two commands in the workshop channel if you are running into errors.
What does yours look like? Mine. Okay.
Camera.
Oh, sorry.
Yeah, so you try running it. So you just do like echidna, then template also. And then you should like churn out some stuff.
Is anyone else getting compilation errors that are different to like SOCC select errors when you run it?
So it's no transaction fit. You should have like some kind of like call sequence.
How did you run Echidna?
Hang on. I did CD to the precise one, and then echidna.
I have template. Nice. I still didn't get it, man. Like, Echidna template dot sol, and I just get that.
But this test does. Oh, this is right. Okay, right. Did you receive the call? Yeah, you did.
Okay, less than equal to yours.
No, I think that's it shouldn't, man. Thank you, right? Yeah.
Okay, that's weird. I'll just ask them.
Yeah, I think it's
Whatever, I think it's. Are you doing the next ones?
I'm looking at the next exercise.
All right. Did everyone who installed Echidna get this working and running? Okay, perfect. And I know we kind of provided the solutions to this already, but I do want to kind of explain a little bit more context as to why and how this invariant works within Echidna, and kind of what we're looking at. So I'll open this up to kind of the audience to kind of help me fill in what this property should actually say. So for those of you who got this property running and working, what was the return value for this function?
Balances of Echidna less than 10,000.
Balances of Echidna?
This should be less than 10,000.
Any ideas as to, or how did you come up with this property in the first place? Like, what was your intuition for kind of converting the sentence into this invariant?
The sum of the holdings of the individual accounts should be less than the total supply of the tokens.
Yeah, exactly. So this is a really good example of a simple invariant that we found, or that we thought about in a token, converted from English into code, and we can basically convert it verbatim. So we did say that the user balance should never exceed total supply, which means that if it does, this function is basically going to return false and find a property violation. So this is a very small and kind of simple example of how we can use invariants and how we can use tools like Echidna to help us find these cases. So essentially the property was basically just to retrieve the balance of the user, make sure it was less than or equal to total supply. So what does it actually mean in terms of Echidna? Like how does this property that we specified, how does it actually, or first, how does Echidna look at it? And then what does the output from Echidna actually mean? So from Echidna's standpoint, we specify the smart contract code. So this is our target system. In this case, was our token. We specify the invariant that we want it to uphold. And again, this is regardless of what a user does with your system. So remember, this invariant is something that we require of the system to be true, regardless of whether a user does a transfer, has a mint, has a burn. It doesn't really matter, to be honest. We need this property to actually hold. So from Echidna's standpoint, it's basically looking for any combination of function calls into your smart contract that can make that invariant false. So what it's going to do is it's going to be that monkey or that cat on the keyboard and just randomly throwing inputs at your smart contracts in order to see whether an invariant can be false. So if we go back to the output from running Echidna, any ideas as to why this property failed in the first place?
Underflow. Interesting.
Yeah, underflow? Yeah. So if we take a look at the token code, this is our transfer function. Considering it's using that line that you had to run for SilkC select, that's basically changing your SilkC compiler version to 0.5. This is the version that the code is running on. So this is the version that is subject to underflow. What it basically does is underflows balance of the sender, which is why a transfer of this amount causes our invariant to break. So from Echidna's point of view, it doesn't necessarily matter what the inputs were. It's just Echidna was able to find a smart contract call that would essentially result in the failure of the invariant upholding. Echidna will also tell us the exact arguments that are required in order to make that, to break it and therefore underflow. So in this particular case, it's just saying transfer to a random address, transfer some amount. You'll notice here that the arguments within this box are different. This is another thing to keep in mind with fuzzing, or these randomized values, is that there is a config that you can set in Echidna in order to make it reuse the same values that it has explored before. But for the purposes of live demos, it's never going to actually match. It's going to essentially be random. It will depend on what Echidna was able to explore then. So in this case, a transfer to the 0 address of the amount 1 was able to make it underflow. So if your numbers don't necessarily match the ones that I'm showing on the screen, that's also normal. Before I move on to the next section, any questions about Echidna and kind of how that exercise translated to code, or how Echidna works? So if we change the token as well as the template 0.8, I'm going to change the Solxi select version to 8 as well. And when we run it, this is what you're going to see with Echidna. It's going to try, by default, 50,000 runs. You can, of course, also change this and up the limit. But this pass is basically saying within 50,000 runs, it couldn't find a failure. You'll notice that this will also depend on kind of your exploration and how your fuzzer works. So if you, as I mentioned earlier, if you are using that config setting in order to rely on previous corpus, like previous fuzzing runs, then you'll likely be able to explore more state. But this past is basically saying that within these 50,000 runs, Echidna couldn't find a property violation.
How does Echidna know what functions to test to run?
So how does Echidna know what functions to test? When we define this template, if we're using Echidna in this mode, the Echidna prefix, all it's looking for is publicly callable functions that return booleans with the prefix. So as we add more functions, as long as we uphold with the prefix and the Boolean return, that essentially adds new properties for Echidna to call. So in terms of how Echidna determines what internal, like in this case, like token functions to call, it's because the Echidna contract inherits from token. By that, it can basically call any public function within token, which in this case so Echidna essentially will operate on top of the output in order to figure out the ABI in order to figure out what it can call.
So any public external functions.
Yep.
But when it's view, it doesn't bother running.
So it can call view as well. It's like you can use a view function within like a property, but because it's not going to change state, then unless your property relies on that function, it's not going to activate.
What about if you have a public fallback function? Does it call that too? And if so, does it like randomize the call data or?
Yeah, so public callable function, it's still, that's a challenging one because it, if your function has the, like if your token contract has a fallback, it will still execute, but a lot slower. And so you'll see generally with kind of larger projects where we do rely on callbacks, we'll just manually basically specify this is like a callback that we expect, and this is kind of the mock function that we expect Echidna to call. So Echidna can explore that, it's going to take a lot longer. And so there are ways that we can guide Echidna into kind of executing more efficiently. And that's what you'll see in more complex code bases as well.
Does it also try, like, for example, force funding the contract with like a self-destruct code on another contract, or?
It has the ability to basically check if the, it has some functionality to check whether the target can be self-destructed, but that's something you can turn on and off. So it's basically, if you want to turn it on, then Echidna will tell you if it's possible to self-destruct. Alright, so I'm just going to go into kind of how to find good invariants, because we've seen an example of one invariant allowing us to find a bug, but when you get into really complex systems and kind of more obscure behavior, it's going to be much harder to actually pin down what is expected to happen. So one thing that we generally start with is trying to start small with your contracts. A lot of people, especially if you start to look at echidna integrations in big code bases, what you'll see is like an integration or an echidna test on maybe a library or like a math function. So that's pure math, no state changes. That's generally a really good place to start because you can basically isolate a very small part of your system and be able to think about, how is the system expected to behave. So when we identify invariants, what does that actually look like? It's a lot of not writing code, unfortunately. It's a lot of looking at code bases and figuring out, if I call this function, what is the expected output, what is the expected behavior, and just writing that out in plain English. That allows you something that you can, for me as a security researcher, go back to a client and say, these are assumptions that I think are true in your code base. Can you help me verify if these are actually correct? And for a developer team to kind of be able to have those ideas and bounce them between your team, because your invariants are only as good as you define them in English. You can't possibly write a really good invariant test without actually knowing what your invariants are. And this is one of the hardest steps of the process because we don't think about invariants very often. We don't think of it quite in this way. When we write unit tests, we think of, I send it this input, this is the expected output. That's basically a one-to-one mapping. For example, you call transfer, okay, you expect the balances to change afterwards. Maybe you check total supply has increased, but you don't necessarily think about system-wide invariants that include something like supply or changes in total supply. So this is one example of how we can pull out the mathematical libraries into something that is actually digestible, easy to test, easy to kind of get an invariant suite up for. Something like a math library. If you're taking two numbers, you're implementing addition, then if you send it two inputs, regardless of what order you send it in, the output should be the same. Same with identity. If you're multiplying something by 1, the output should be itself. And the same thing for inverse. If you do one operation and then you do something that's basically the opposite, so addition, subtraction, multiplication, division, the output essentially should be 0. So system-wide invariant is basically that the system shouldn't have changed. If you look at the system kind of before this operation and afterwards, the states should be identical. I kind of threw you in the deep end for this token one because I kind of gave you the invariant to test. But this is these are other examples in which we can actually look at how to think about invariants. Obviously, no user should have a balance that exceeds total supply. That's one that we've harped on for a little bit. Another one is for transfer, that the sender balance should decrease and the recipient balance should increase. Now this one is pretty intuitive. If I'm transferring funds, my wallet balance should not be less than it was before. Again, if I try to transfer funds to myself, the balance should be the same. So these are, you'll notice that as I kind of talk about invariants, there's a difference in kind of the type of invariants, because some of them are function specific, some of them are kind of global to the system. So that brings me into identifying what your invariant is actually supposed to target. So if you're looking at a functional invariant, this is, I call the add function with two numbers, and this should be identical to add regardless of what the order is. Another example is if I were to test a math library, pretty much generally any math library is generally a functional level invariant because because it's something that's stateless. We can very easily craft a scenario, basically setting up a scenario in order to test kind of the expected behavior. Now, the other type of invariant is a system level invariant. And this is something, for example, like user balance and total supply and kind of their relationship. These are generally stateful. By stateful, I mean literally changing Ethereum state, something like balances. For something like a token, that contract is relatively small. But as you start getting into bigger code bases, especially the bigger they are, the more complicated your system level invariants are going to be. So for Uniswap, any ideas on what a system level invariant might be for Uniswap?
Constant products.
Yeah. So Uniswap relies on basically a concept of the constant product. So it relies on essentially after every swap, after every swap, it's going to check an invariant that's basically K. That's kind of the colloquial term. Without going into a whole lot of detail about how K is calculated, Uniswap operates completely under the assumption that K is maintained to be monotonically increasing for every operation. This is just expected behavior of Uniswap. This is something that's built into how they are expected to function, and this is something that needs to be withheld in their entire system. So this is another kind of example of invariance and kind of being able to pick out what is expected behavior of these systems. So if we take a closer look at what a functional level invariant is, a functional level invariant is basically allows us, this is a code example of the commutative adding property in that A plus B is equal to B plus A. This, you'll notice, in this case, inherits from, let's just say, a math library. It doesn't really matter what kind of math library it is. But it inherits from a math library, and this test commutative function, this test looks slightly different to the one that you were interacting with before. The one before had the echidna prefix and returned a Boolean. This way of specifying invariance in echidna is basically to specify invariance through this assertion. So if you're not familiar with assertions in Solidity, they're basically require statements, but in terms of development, tools like Echidna will look for assertion failures. So essentially, think of this as if Echidna finds a failure within this commutative adding property, Echidna will throw an error similar to the one that we saw in our terminal earlier. So this is just another flavor of interacting with Echidna, where we can essentially set it to assertion mode. Now, one benefit of assertion mode over kind of the property mode that we saw before was the Echidna prefix. Assertion mode allows us to test multiple things within a single function. So if we look at, for example, if we look at that example with testing token transfers, then we can, with the Echidna prefix, we would be limited to only testing something like total supply. Whereas with assertions, we can now test sender balance, recipient balance, and kind of add on additional properties. Now, system level invariance, as I mentioned before, this is where things start to get a little bit more complicated, and this is definitely not going to be the focus of today's workshop. There are many ways that you can kind of implement system level invariants, and a lot of them do hinge on either construction, so you're basically setting up the system, something like the Uniswap core, Uniswap factory within the constructor, or you're relying on deployment unit tests to basically set up your system and then start testing on top of it. So with all of these, in all of these cases, Echidna is going to look for that public keyword within basically all the functions that are public, and Echidna is basically going to call them and trying to integrate any variation of calls that will result in a system failure. This is one small example of a system level invariant, is the one that we did related to token balances. Now you'll notice this is showcasing a slightly different way to use Echidna in that assertion mode, and it allows us a little bit more room kind of to specify what and how we want to configure it. So we can run that. We can basically run this with Echidna as well, just with so if we were to set, remove the public return, basically assert then when we run Echidna, I'm going to revert this back to 0.5 for we just add test mode assertion. This tells it to look for assert statements instead of the default, and we need to run sources. Basically going to find a similar output. Now the only other thing, it's going to run assertions on all of your publicly callable functions, which is why you also see additional functions down below. So this is basically looking out for assertions in all of the functions, all the publicly callable functions within that were inherited from the token. I know I've talked a lot. Any questions about kind of those invariants and how Echidna works?
Okay, so what if the barrier actually could be break if certain external dependency is sent? For example, you mentioned Uniswap core. The constant product will be break only like you integrate the inflationary token or rebase token. So does that even covered by the Echidna, or this should be an assumption of the integrated token on the behavior?
Yeah. So that's a great question. So the question was whether Echidna could handle, or whether Echidna handles something like a rebasing token for like Uniswap. Echidna will only explore the paths which you define. So if you specify, if you set up the entire system working with a traditional non-rebasing ERC20, then the assumption there is that Echidna cannot find potential invariant failures with the rebasing token. That being said, if you do rework kind of the deployments and set it up with the rebasing token, it will also depend on a variety of different factors, like especially with something like Uniswap, it's something that you'll want to essentially save a state every time you run Echidna, and it will take quite a lot of coverage in states in order to find those invariants. So I think it kind of goes back to they're only really as good as you set up the system. So it's not going to find anything outside of your domain.
So is there any way to use the fourth state of the third mainnet to be the foundation of the test?
It's in the pipeline.
Okay.
Yeah.
Let's say there are multiple contracts that are kind of connected to each other and maybe have special access to each other's methods. Can I, with the system level invariant, can I tell Echidna, oh, don't just explore calling this contract, also try calling methods on these other contracts? Will it only ever try running calls in the contract that is also on the base?
Yeah, that's a great question. So in the previous examples, like for example for this, it's only going to explore public functions on the token. If you do set up Echidna with like a deployment script, and the deployment script say creates like a factory and like multiple pools and whatever the pool depends on, then Echidna will essentially explore anything that's public or external on any of those contracts. Now that being said, especially if you're running in an assertion mode, the output that you're going to get is going to be way bigger than these assertions that you see. And so Echidna also has the ability to say, we also have the ability to basically say, ignore fuzzing like these certain functions so that you can kind of isolate the system in ways that you choose. So it will basically, if you do set it up with a deployment script, then it will call any publicly available.
Can I specify, like, for these arguments in the test mode, we have like this parameters where it chooses randomly from the whole space, I guess. Can I specify like constraints? For example, let's say one parameter is an address, and I only want like certain addresses to be tried, or maybe I have two numbers, I only want the second number to be smaller than the other one, something like this.
Yep. So yeah, there's a variety of different configurations that we can specify. One thing that we'll be looking at with exercise 2 is how to bound your input ranges. But just to provide a sneak peek, you can also use traditional Solidity require statements or just like modular checks here. So one option is you can just add a require and say, if you have a function that takes an argument, let's just say UN balance, you can actually bound it and say require balance is like less than 20, for example. So you can use essentially your Echidna test to bound your inputs. Like if you want it to be, one or two values, or you want it to be certain addresses, then you can formulate essentially what those inputs are before you actually invoke your function call. And this is a slightly different example than like these assertions. This is assuming that you would do something like call like the transfer function afterwards, for example, with like the balance argument. Any other questions?
One more question. Can I expect a reversion in my test? Can I do a test where I say, oh, this should revert like this?
Yep. Yep, you can test reverts as well. So you can do that using, Solidity has a try-catch statement. Assuming that that's one way to do it, you can basically wrap your call in a try-catch, and if you expect something to revert, then you can actually just assert false in the case where it was successful. The other option is if you're using like a low-level call, you can basically invoke the call and just get the success value and the return data out. And then you can check on success as well. Alright, so exercise 2 is going to be a bit more involved, a little bit more hands-on. I'll walk through kind of what exactly the contracts are checking right now, and then I'll give you an exercise to fill in as well. So before we get started, I want to kind of walk through this library. This library is based on kind of a reserve library. You don't need to know a whole lot of details other than it holds the reserve of 2 tokens, as well as the liquidity of tokens. It has the ability to swap. So basically, if you take 1 token, you can essentially, depending on which direction you want to swap, it's going to either decrease or increase the amount that you swap with. It has the ability to add funds. So again, this is a library, so we can make the assumption that there is a wrapper for it. In some other place where it actually takes the input of tokens. This is just a stateful library that basically just changes internal balances. What it does is calculates essentially how much liquidity to add. It takes the minimum of either one of the 2 tokens, and then it changes balances within the storage. So by this we can basically say, okay, add funds does some rough calculation, and then increases the amounts of both of your tokens as well as your liquidity. Remove funds basically does the exact opposite. It calculates how much, given an amount of liquidity that you want to take out, how much of each token should be adjusted, and then adequately decrease the funds. So if we open up template, one thing that we can kind of think about within kind of how this even just add funds function works is to think about what are the preconditions, what is the action, and what are the postconditions of this add funds function. So if we go back to liquidity tracker, let's take a look at add funds. What is a potential post-condition of this function? What is expected to happen once this function runs?
The reserves increase.
Yep, reserves increase. Are there any preconditions of this function? Usually tell by the number of require statements in it. So because there are no require statements in this function, there are no preconditions. This function can be called at any point. Right, that's a good point. Reserve risky and reserve stable cannot be 0 because once we operate on this division, it will essentially revert with the divide by 0 error. So to an extent, we can basically say the preconditions are that reserves are not 0. Action is basically we can call the liquidity tracker in the add funds function. Basically, we expect the reserves to increase. So if we were to be more specific about that, we're basically saying that the reserve risky, stable, and liquidity should increase. So I'll give you 10 minutes to fill in these preconditions and these postconditions. The way that you run this is the same as the last one. The one thing that you might need to do is install the latest version of Soxy Select or Soxy for 0.8. It's a different version if you don't have it installed already. And then you should be able to do running this version is going to be slightly different than the previous one, just because it's in a different API mode. So I'll just post the exact command to run it. But we're basically invoking Echidna on the file and specifying that we want to run this specific library with a test mode of assertion. But I'll post this in Discord so you have the ability to see it well. And if you pull the latest version, you'll also find those commands on the top. Just Soxy select use, how to run a Echidna.
transaction or each like in a separate transaction? Or?
So if you have it in the same function, it'll be within like that same transaction. But if you have it like split up across multiple functions, then Echidna can explore it like across blocks.
Yeah, because some have, for example, like a self-destruct doesn't take effect until the end of the transaction. So if you want to test the effect of a self-destruct, like destroying something first,
Yep. So as long as your post conditions are in the same function, you would be able to test that.
and is there a way to like set some metaparameters, like set the block number to a specific value, or the block hash, or the Coinbase?
I would have to check on that. I know there are configurations for like sender addresses for sure for block numbers. I'm not 100% sure. I can check with that. Generally, you can manipulate. You can generally manipulate the VM pretty easily. So.
Can you test events?
Yep, you can. Well, I should say you can get event emission, but Echidna is not going to like test on like the output of an event.
Actually, I haven't been trying to do it because I feel like I haven't been doing the exercise.
It's okay.
Yeah. My brain's a bit down now. I think I need
Yeah,
coffee.
you arrived quite late yesterday, right?
Yeah, 3 a.m.
Yeah, I understand. Like,
I think I need coffee before the next war room, man.
okay.
Give you about 3 more minutes, and then we can walk through the solution, and then also kind of walk through a few more features of Echidna that might be useful for debugging.
Can I ask you a question? Maybe for later. I don't know. I was wondering, when would you choose to use Echidna
Yeah, that's a really good question. I think for generally, like Echidna is in some ways a little bit harder to set up, but I think the part where it becomes really kind of clear, the output, the difference is that for something with Foundry, it always executes within the same block. So all of your fuzz transactions are basically within the same block. So Echidna will allow you to essentially call these functions across many different blocks. And so you can test really complicated exploits without really needing to do a whole lot of setup because Echidna does that out of the box.
You could like skip or something.
Yep. Yeah. Also, Echidna supports like crank and all the VM operations.
So you could use the same.
Yeah, exactly. Exactly. So pretty much anything that's implemented within Foundry can pretty much be run on Echidna. Yeah, yeah, sure. Alright, for those of you working on those post conditions, do you want more time to kind of iterate over those? Alright, I'll go through it in about 2 or 3 minutes then.
How do I specify the number of runs?
Yeah, you can do that using test limit.
So it's like dash dash.
Yeah.
Okay.
Escape it. Yeah. Dash dash test. Yeah. And then your number.
Okay, thank you.
So another thing to note, if you do want to increase your test limit for these iterations, you can also you can do that through your CLI through test limit, and then a number. And this will essentially increase your runs up to the number you specify. Alright, just to walk through those preconditions and postconditions. Our preconditions was basically that the reserves should be initialized with some value. You will find this setup reserve function already there. So what the setup reserve function does is basically sets up these 3 values with some number and sets the is set up to true. Which means we can use this to essentially determine whether the system has been set up yet. I'll come back to the precondition for this because I think it's clear afterwards. But if we start looking at the action, what we want to check is basically that the reserves have increased, that the reserve risky, stable, and liquidity have increased. So how we can do that is basically by first saving a state of what exactly are the liquidity values before the transaction. So given it's using liquidity tracker data, we can basically just declare liquidity tracker just say this is the gives us a snapshot of what the reserves are before the add funds is executed. Now, how do we check whether reserves have actually increased? What would the syntax be for that? If we have an assert, what should we be asserting?
The reserves after is greater than before. Like all three of the columns.
So what would the syntax for that be?
Dot. Reserve whiskey greater than pre at funds call.
Yep, and then we can basically repeat that for pretty much all of the function call or all of the state variables, including reserve state. Now, if we go back to the reserves are non-zero, we can actually make use of the Boolean that we've defined, whether the system is set up or not. So the simplest way to do it is if the system hasn't been set up, then just call setup reserve. This is what I mean by we can craft. This is what I mean by we can craft scenarios that essentially allow us to test a setup system easily. So in this case, we don't necessarily need to have that initial transaction to increase your reserves. We can essentially assume that that has already happened through something like this. So if we run that, so while that runs, any questions about the implementation or the syntax of these? Sorry? Do you mean you're getting an error message? Yes.
Can you post that comment on the?
I would just miss the flag.
Yes, I will read.
他就要加点东西让他飞。
Why are these methods, these test methods, they're returning like I don't know, some new values or some before was always just a boolean. Why do we have to set return value to this?
Yeah, that's a good question. In these functions, we're returning values, and in the previous ones we weren't. This is just a sneak peek for kind of a future exercise. In the current, right now we can actually just remove everything afterwards, and essentially it would behave the same way. Because we're specifying assertion mode, Echidna is not actually going to look at any of the return values and what their values are. It's only going to look for assertion failures.
It's time for the warning, right?
So if we take a look
It's
at
here.
our Echidna tests, we can see that in this case, we had a failed assertion, and it failed because when we called add funds with 0. Now, this doesn't give us a whole lot of information to go off of. Yeah.
Just a question. Before you said that all the input is like randomly chosen. Now here we have 2 zeros, which has 0, like I don't know which is set. So are there certain values like max 0 or 0 that it always right?
Yeah, so randomized is kind of simpler than it actually is. It will start with kind of the ends of your input. So generally 0, your max U256, or your type. And it will depend, if you do have constants defined in your code base, it will also use those as test cases first. So it will essentially test on the known bounds of your input first, before it starts to kind of iterate. So again, this reserve add funds doesn't give us a whole lot of information as to why it's failing and what caused it to fail. And so for that, we can actually make use of this assertion failed object or event, which is defined in Echidna. Will essentially look for instances where we're emitting assertion failed and give us some concrete information. So if we take that, then we can basically just convert these like assertions into a slightly different syntax. So if these are true, then we can emit assertion failed. Even just like with the message, specify reserve risky and like the pre-call reserve risky, and we can basically do that for all of these. Which allow us like a little bit more information as to why exactly this failed. So instead of specifying reserve stable, we can specify liquidity. Basically say that the liquidity doesn't match. If we run that, then we get a lot more useful input. That's kind of different and more intuitive than just 0, 0. What we can see is kind of 2 failure events. Because Echidna is looking for instances where we're emitting this assertion failed event, it will essentially halt whenever it sees the event and tell us about a failure. But more importantly, what it gives us is the event stack trace of the string that we specified we wanted this to emit, the pre-balance, post-balance, and who the sender was. A sender doesn't really matter for our purposes, but basically this this test case is basically saying we added 1 token, and from the output, the post-balance of the stable token didn't actually change. Any questions about kind of this output, or any ideas as to why this actually happens? Yeah, exactly. So this is one case in Echidna where it essentially notified us of a rounding error. Now, again, this is probably something that could have been detected through manual review, maybe manual analysis, but this gives us a very easy output that we can actually see what the expected behavior was and how it differed. So this is another example in which we can actually make use of these invariants in order to find kind of those small rounding, or they look like small rounding errors, but eventually they will add up and could result in protocol loss. Now, I know there's a few other functions within the reserve, remove, and then the addition of funds. We're probably not going to have time to go through these exercises today, but I do recommend at least trying out for yourself, kind of writing those preconditions and those postconditions for the rest of these two functions, because it gives you a better intuition for this small code base, how to write them, so that you can apply that knowledge to other code bases as well. Now, I did also provide solutions to kind of the add funds, and that's where the return value for the add funds function comes in. You can actually make use of those two functions when you write the invariants for this last one. So I'll open it up to questions just about fuzzing in Echidna before I enter the last section.
How different do you think the fuzzing in Echidna is to boundaries fuzzing?
Yep, that is the next section.
All right. Now again, it found like the 0, 1 value.
Yep.
It's probably not coincidence, but 0 is the 1. So 1 is also a special value that it tries.
So Echidna relies on heuristics in terms of like how to find those inputs. So it'll generally try at the bounds, so 0, give it 256 max, and then start inching its way closer to kind of the midpoint. But there, again, it kind of changes if there are like constants defined in your code. So if you say define like a constant, one common example would be a number of decimals for a token. That would be another magic value that Echidna would be able to use in order to call your code, in order to call your functions. So it kind of relies on a variety of different factors in order to kind of maximize the number of tests that you're running when you run that fuzzing campaign. The other thing to keep in mind is if you enable essentially coverage saving within Echidna, every time you run, and so every time Echidna, once it's done, it always says campaign complete. Press escape to exit. If you enable the corpus like coverage saving, another step that it does at this stage is basically save the covered state of all of your contracts, as well as like magic values that it found like useful or productive, so that the next time that you run it, Echidna can essentially execute off of existing state.
I also noticed that, like earlier in the first example, I tried out to test to say like an assertion, I don't know, the user's balance is unequal a specific value, but Echidna had problem like finding that even though like if you had like if you set it as a magic value, it would have been pretty obvious, but it doesn't use anything that you use in your test or inline variables that you set. Or is there a feature that you can activate or more static analysis or something to be included in the identification?
Yeah, definitely. There are definitely a variety of ways that Echidna like finds those inputs, and generally it works better on ranges as better in ranges than like specific values. That being said, there are like certain cases in like complex deployments in which some of the those constants that you define should help the seed. And if they don't, that's likely a bug within Echidna that it's not actually picking up like the specific values that you've defined. So in terms of kind of execution, the idea is that we should be essentially relying on constants that are defined. Alright, so going into kind of a comparison between other similar tools, I think generally a lot of the questions that we get are kind of Echidna versus Foundry, and in kind of different areas of program analysis on smart contracts. So in terms of Foundry and kind of other fuzzers, one area where Echidna kind of helps is that it doesn't really necessarily matter what development framework you're using. It will work with pretty much any existing framework out there. So if your tests are already in Foundry, your deployment scripts are already in Foundry, Echidna will work with that out of the box. It's possible that something like Foundry might be easier, kind of easier to pick up when you first write your tests and kind of especially your stateless tests. That being said, Echidna also allows you to essentially run your, Echidna has a Foundry mode that allows you to basically run existing fuzz tests that work in Foundry on Echidna as well. And one benefit that you get out of that is that you can basically use like the vm.prank, etc. of syntax in Foundry. And with Echidna, you'll be able to test not just per transaction in a block, but you'll be able to test across blocks. So that kind of gives you a little bit more power in terms of cases and corner cases to look out for when you're testing your contracts. So the other approach is kind of the formal methods approach. And this is something you'll see generally with Manticore, KEVM, Satora. And for a lot of these, they will provide proofs. They will, provide kind of concrete proof that your code behaves as you expect. That being said, it is generally more difficult to use, and it generally takes a lot more ramp up, whereas fuzzing is something that you can basically pick up with because you already know Solidity. It's relatively easier to kind of extend your Solidity like unit tests or just fuzzing in general, given that it's within the same framework. Echidna also has the ability for you to test either functions that consume a significant amount of gas, be able to differentiate which functions especially are gas costly, and be able to essentially analyze where a lot of that gas is being used. It supports differential fuzzing in that you can test against like a reference implementation or implementations in other languages, and generally works with any compilation framework. So behind the scenes, Echidna relies on output from Slither and Critic Compile. These are both Trailbit's external open source tools as well. And what those do is basically kind of provide the input that Echidna would need to execute. It also has a variety of APIs. We saw 2 of them today with the Boolean property, with kind of that Echidna prefix, and then the return value. It has the assertion mode, which we saw in the second example. The assertion mode is kind of something that gives you the ability to test multiple kind of assertions within the same function. And then it has dat test and Foundry mode as well, which you can essentially match syntax with that. I guess in conclusion, the Echidna, we have quite a lot more resources and kind of examples that you can continue to work off of and kind of get a feel for not just how to write invariants, but how to think of these systems in general. That second example is just one part of something of invariants that we saw. And I definitely recommend going back and kind of implementing the post conditions for the rest of those functions and kind of seeing how you can not just implement post conditions, but also how you can make use of multiple functions when you define these invariants. Generally, because invariants are so complicated in terms of just thinking about your code differently and kind of requiring a slightly different mindset, one way to get started with that is just to write down pretty much what all of the expected behavior of your code is, expected behavior of your function. Start with just writing it down in terms of words, and then work on essentially validating and verifying that those invariants are in fact true before you even start thinking about touching code. One thing I do a lot is sit down and start hammering out invariants, only to realize that you got the invariants wrong and you have to rework it. Now, that's also another thing that there are cases in which you'll be really confident in an invariant, you have a failure, and then you find out it's because we were missing a precondition, or that we didn't set up the system properly. So writing invariants in general is kind of that iterative process of really getting a chance to kind of iterate over first defining it, writing in code, and then kind of, if you do get a failure, trying to figure out why exactly it failed, and then if it's something with your test, adjusting those tests. So I'd highly recommend continuing to build off of exercise 2 in the two other functions, as well as try out Echidna on your projects, and also to take a look at so if you also want to see more complex use cases of Echidna, these property testing suites is a really good resource to use, so that you can kind of see how these large projects have picked up Echidna and what their invariants look like. Any questions about fuzzing or anything?
Besides the build secure contracts repo,
Yeah.
is there any other Echidna resource that has exercises?
Yes. Aside from building secure contracts, there are some exercises there. There's also Echidna streaming series. I can post a link to this as well, and I'll add it to these slides. In here we have 6 Echidna streams. All of them essentially, they kind of start off from the basics of how to fuzz, how to think about invariants, up until how to essentially implement Echidna on a complex code base. All of these have exercises associated with them. And there are a few other repositories that also have kind of more hands-on experiences with writing invariants and then determining. So I can share them afterwards.
About Trail of Bits process, like audit process, do you, like, Echidna is really like an essential part of the audit process?
Yeah, definitely. So the question was around kind of Trail of Bits' kind of security review process. So a lot of our security reviews, we try to use Echidna and kind of these tools as much as we can throughout kind of the audit. Generally what we'll start with is running something like static analysis on the code base, like Slither. That kind of gives us an idea of just low-hanging fruit. This is something that, again, it's very verbose. So it tells you a lot of information, but it requires you to kind of go through and check whether they're actually valid and actually relevant to the code. Once we do kind of the static analysis piece, a lot of it goes into manual review and kind of understanding, okay, if we are looking at a system, how is it expected to behave? And this is generally when we can start thinking about invariance as well. So the manual review and kind of the invariant finding is generally something that I at least do kind of in tandem. And then depending on kind of the infrastructure and time, what we'll either do is deliver a list of invariants. So these are the list of invariants that we came up with during kind of our review, and these are something that we can kind of provide support for in terms of integrating Echidna, but not necessarily do that during the specific audit. But in generally longer audits, we'll do the setup and essentially have be able to give that to a client so that they can continue to have that running in like a CI every time they start to add code and change code, so that that's something that they can continue to build off of.
Thank you.
And there's not necessarily a clear delineation between when the manual review stops and when the Echidna starts. Generally, we'll really bounce between the two. Sometimes we'll kind of go into Echidna and realize we started too early because we don't actually understand the system yet, and then we'll go back to manual review and kind of pick up the program analysis piece afterwards. So it does take a little bit of practice in terms of identifying what area to start with Echidna, especially when you start looking at these complex projects. The biggest challenge is really trying to identify what you should be testing with Echidna and when is kind of the big piece.
On the agenda to add like support for running against like a certain state of a mainnet or whatever. How close is this? Because for me it seemed like if I have a protocol that maybe integrates with I don't know, Uniswap, then for these tests to work I'd have to do a lot of manual setup in my tests. This is like something that's close or.
Yeah, so the current infrastructure for as you saw with like deployments, it's going to take a lot of kind of deploying like the factories and the pools and kind of everything associated with it. That's kind of a work in progress in terms of just how to kind of formulate and kind of set up everything as a package. One thing we didn't necessarily talk about today was the ability to seed off of deployment scripts. So like if you think about any kind of project that has like the essentially either testing deployment or like contract deployment, what Echidna can do is basically snapshot the blockchain after, so assuming that you have like a local blockchain running, you can run the deployment scripts against that local blockchain, and then Echidna will save the snapshot right afterwards. And so from that, you can basically start testing kind of more, at least complex code bases locally. That's one thing that already exists, and that's one thing that we use pretty frequently. But the kind of more complex integration requires a lot more kind of, not just, requires a lot more kind of configuration and details there.
You said that you can also integrate with like crank calls from Solidity, from Foundry. So I guess you could also use like set code or set storage to manipulate like for example, just copy code over the code by.
Yeah, exactly. So anything, all the syntax that is available within like VM rank, etc. You can run that on a kit. So pretty much any of your boundary tests you would be able to run in a state in Echidna as well.
Very quick question. So, sorry, you might have already covered it. I think recently in rolled out the mainnet support, I think, right? Just wonder, in general, like, what's the, is there like limitations to it, or is there, like, how to best use it?
Yeah, I think we're still, so you can point Echidna to the mainnet fork. We still need to work on kind of additional documentation on kind of how to use that the most effectively. In general, it is kind of the first version that we've pushed out for mainnet, and this is kind of still a bit work in progress. So it's definitely something that we need to flesh out a little bit more.
Ha ha ha.